So, my name is Hayato Saigo, and this is, I think, the last session of this afternoon session. My talk title is a very large scale title, and someone knows that this is some mimicking the great Isaac Newton, mathematical principles of consciousness science, non-commutative probability and categorical structure. So this is abstract. The point is that the fundamental question of the mathematical principles of the consciousness science is the mathematical, how do you define the notion or mathematical counterpart of the state of the consciousness? I think it is still unsolved. In this talk, we propose to consider the states of consciousness as linear functions on category algebras. Thanks to Masanao, yesterday's talk, Masanao explained very clear-cut explanation of the category algebras, but maybe it is a bit difficult for the mathematics beginners. So I will try to introduce this notion more conceptually or naive kind of intuitive introduction. So more precisely, we propose the following working hypothesis. One, the brain activities and relationships between them focus a category. Maybe I should use this, maybe. Okay, category. And the elements of category, then category gives, as I explained, the category algebras, which is observable algebra reflecting the categorical structure. This is intuitively, category is a generalization of space-time. And this category algebra is observable algebras reflecting the space-time degrees of freedom. For example, it's typical example. This is a quantum field. And the interrelationship between the brain and its environment defines the state on the category as a conceptual level, and the mathematical level, it is linear functional on the category algebra. And this state, very abstract, seems to be abstract, but corresponding to the map from arrows to the expectation values or the intensity of them. And this interpretation is not in with mathematics, just to how to connect these abstract notions to the experimental setting. And the state on the category as a linear function of category algebra is a state of consciousness. Of course, this is a kind of interpretation. This is the phenomena and mathematical model. Okay. It may unite neurosciences, cognitive sciences, especially quantum cognition, and consciousness studies in terms of category and non-commutative probability. In mathematics, these two branches of fields called category theory and non-commutative probability is considered a very different field. Of course, it has a many relationship, but this relationship seems not to be direct one. But I found, I think, the direct relationship, and maybe it is worth introducing here. Okay, so the first, the definition of category. I suspect that no one defined this notion in this workshop. But the category is, roughly speaking, a system of two kinds of entities called objects and arrows. Object is this kind of thing. It can be anything if it satisfies actions. And arrows also, anything, but even if it satisfies actions, but the image is, the arrow is some kind of processes. Not only mapping or something or relation or something, more general kind of process, a kind of dynamics or something is can be the notion of arrows. But arrows should be equipped with a domain and codomain. Domain means just the starting point of arrows, and codomain is a targeting point. And the important thing is the category has to have the structure called composition. This is if the arrow is in these kind of neighboring arrows, then you can compose this as then generating new arrows. So and also there is an identity arrows called the special kind of arrows called identity arrows for each object A, 1A I denote. And this composition should satisfy the associative law. And also this should satisfy the identity law, like this do nothing, G do nothing to G, do nothing to F. So we can identify these objects as identity arrows as a very mathematically, if you, without confusion, you can think of this object as a special kind of arrows called identity arrows. So in short, category is a system of arrows which can be composed. Okay. So in some trends in the category theory, this arrow kind of pictorialism is not used in modern kind of monoyar category. How to say, sect use this notation, but I stick to here to for the beginners. Okay, so then if you consider one category and another category, the natural thing is to connect or making the correspondence between these categories. So not the mapping, only mapping on objects, but also the mapping on arrows should have been considered. And also just mapping, but the structure preserving map is needed. So what is the structure of category? That is nothing but this composition kind of thing. So this should have been satisfied. This correspondence is called functor. Okay, so any kind of analogy, model, or the interpretation or theory, it can be considered as a example functor, but I omit here. Okay, so this is almost all the almost the same figure, but just changing the order. This kind of thing is called contravariant functor. So in this talk, special kind of contravariant functor on one category is important, which is called involution. This is a definition of that, but the point is this operation is just taking one arrow to the reversing kind of arrow. But this reverse is not like a group multiplication and division kind of thing. So here and here does not have to be the identity. Here and here, this composition does not have to be the identity. So it's like a journey. Journey is the arrow from one object to the same object, but the journey is not equal to stay here. So Dagger category is very much like a group-like, but not only one object, and this does not have to be the real inverse. Okay, so this is a short, broken introduction to the category. And the next, this is one main point of this talk. The notion category algebra. What is category algebra? It is very intuitively speaking, the algebra generated by the arrows as indeterminates. So how to say the indeterminates is in high school mathematical language letter. Letter means X, Y, Z, or something. X, Y, Z does not have the definite value. So it is itself X, Y, Z. But you can multiply X, Y, or Y, Z, or Y square, or something. As that, we can think each arrows in category as a letter. Letter means you can make this kind of thing, A plus C plus BI or something. But the point is, this is very easy. But the point is, this A, B is some kind of number, then it is very simple. But the point is to define the product is a very difficult. But it is a canonical way to define the product. But this seems too complicated, but the idea is quite simple. If the arrow is in this kind of pair, then the product of the arrow is this. But if the arrow is not connected, the product is 0. This rule of thumb can give you the how to say the bachelor of category algebra. Okay. So this is and some people, mathematicians, are interested in this thing, but you can think of this just a complex number here. But you can generalize actually, not necessarily have the negative inverse or the commutativity or multiplication, but you can think of the complex number or something like that. This center is related to your top the central, but I omit here. And this is very long, but intuitively speaking, you can think of the vector space. So for general. And you can think of the very nice algebra. Algebra is very general noun in usual lives. Like a high school student knows algebra or geometry or something. But here, algebra is a technical term. Algebra is a vector space equipped with multiplication. Do you know such an example? For example, the complex number itself is the very nice example called algebra, but you can have many kinds of algebras here. And operator algebra, shift algebra, something is also called the algebra. So the category algebra is defined as follows, and I think some mathematicians are interested in the very technical point. You can define these kind of products, and interestingly, it has a multiplicative unit, which is this is for object or identity arrows, you assign 1, weight 1. For other arrows 0, then this becomes a multiplicative unit in this algebra, even if the objects are infinitely many. Okay, so as I explained, the idea is very simple. So by identifying this arrow C to the iota C, which is the element of category algebra, you can calculate this like C equals, for as I said. In short, the category algebra RC is an algebra of function. This is, you can think of these complex numbers. So this C is a system of arrows, which is not numbers. Which is the very, how to say, the letters, indeterminate. And this is a coefficients. So making the together the process and numbers. Process means some kind of how to say qualitative nature or relation. So Aristotelian category, then the quantity and quality and relation is modeled by C. And this is some more quantitative or the number kind of thing. So you can calculate this kind of thing in the exam. Okay. So this is category algebra is very interesting. The generalized notion of matrix algebra, but I omit here. And if the category has an involution, especially the so-called dagger category. Dagger category is a category having involution which conserve the objects. Then it is called dagger category, and dagger category has many important examples. For example, as Okamura says that the networks, the graphs generate the dagger categories, and also the manifolds. The points of manifolds are objects, and the path between the objects is arrow. Then you have the dagger category. So just forgetting such kind of thing, just you can start from the dagger category. So then you have the space-time structure. But in this kind of dagger category, we have the involution on algebra. So category algebra level, in category algebra level, you can have the star algebra structure. Star algebra structure as introduced by Masanao and Kazuya. So this is a generalization of Hermite conjugate, like a complex conjugate or Hermite conjugate or such a thing is generalized into the very general category algebra. Okay. So the point is why we need this is it has very deep reason, but very, how to say, simple reason is to define positivity, we need this. So why positivity is important? This is related to the probability interpretation. To assign some probability meaning into some numbers, quantities, we need to have the notion of positivity. So if you are given some star structure, star algebra, then we can talk about the positivity structure. Then we have the notion of state on category. State is a linear functional defined, or positive linear functional defined on some star algebras. So it means that this state is nothing but a statistical law mapping each observable quantities into the expectation value. If the random variable have to be the positive, then its expectation should be positive. The other special cases, 0, 1 valued random variables, the expectation value is equal to the probability. So probability should be positive. So this, if you admit to this kind of condition, we get the notion of state in general on star algebra. But now, so this is a general definition of state. If you are given star algebra and some leaks, for example, the complex numbers, the state is defined as an expectation function, e to s. This is linear. That corresponds to the expectation should be linear. The positive thing should have the positive expectation. The do nothing thing, so always one kind of thing, should have the one. So the pair of these things is called non-commutative probability space. And this is a basis for all the so-called non-commutative probability. But in this case, the important thing is the meaning of the state algebra or something. So this algebra is, in a sense, intrinsic nature of the system. But intrinsic needs some explanation. The construction of the intrinsic nature of the system can be exhibited by some kind of transformational structure. Like as Masanao explained yesterday, that we have a measurement, we have some kind of symmetry. Then you can suspect the structure of the hidden, the deeper level of structure of this system, intrinsic, so-called intrinsic system. But it is not sufficient to describe the system as it is, because a system has a interrelationship between environment. Then this interrelationship determines this each state. So this is a non-commutative probability space if it embodies the statistical nature. Okay, these are just as it is. Yes, I explained this. Okay, so then the notion of state-on category comes. This should be named state-on category algebras because the state is a linear function defined on the algebra. So it should be algebras. But from some sense, it can be abused as a state-on category because we have this kind of theorem, which seems to be complicated, but it just say that to define the state is the equivalent to define the weight on arrows, which has some kind of positivity conditions. So in complex cases, its value don't have to be the positive, but some generalized kind of positivity notion here. So in quantum mechanics or quantum field theory case, this kind of positivity condition is very important. So conceptually, the theorem about means that states on category with involution with finite objects are nothing but here I proved for the finite object, but you can generalize it. But the feature generalization probability distribution on a set as a discrete category. Discrete category means the only object is there, that all arrows are identity arrows. This is called discrete category. Category like this, no intertwining arrows. In this case, the state is nothing but the probability distribution on objects. But this generalization for there is many intertwining arrows goes to the non-commutative domain. So more generally, we can say that to define state-on category whose support is contained in a subcategory with finite object is equivalent to define the corresponding function which assigns a weight or intensity or expectation to each arrows. So each state gives a corresponding representation of category algebra, category in the context of Hubert space as a GNS construction he introduced. So I think this apparatus is very important for this kind of thing. Okay, I omit here. So this is a CM commercial. Yeah, our working hypothesis. So the brain activities form some kind of category. We don't have the definite candidate for this category, but I am sure that we can define very good category from the Korea structure. And then you can define the category algebra in canonical way. And I think this is correspond to the Korea kind of thing. And the interrelationship, the brain and its environment to define the state of the category correspond to the map from arrows to the expectation values so their intensity. So this mathematical state on the category is a state of consciousness. This is my hypothesis. So yeah, in one picture, I express my ideas. So okay, I will skip here. Okay, so this is a reference. Thank you for your patience. Yes. Actually, if you are given some data category and another category, then we can construct the category algebras. So this is a category. Here, the category of categories. Here, category of star algebras and the CP map, completely positive map. So you can make this correspondence. So this structure reflects the structure of algebras. Then we have the many studies in operator algebras or quantum probability. We have many information here. Information means studies here. So making for example, the identification of my category and the other category or the animal category or something is can be translated into the sameness of the non-commutative probability space. So if you can have these like instrument using instruments, for example, the modeling our structure or the dynamics on that, we can consider these kind of the sameness by using this kind of thing. So this is a completely positive map, which is also treated in the Okamura's talk, and this is quite fundamental in information, and Masanao characterizes the completely positive instrument is physical instrument. So this is very important notion, but very interestingly, as Steve pointed out, the Okamura's in Okamura's talk, a star kind this is very important, and it seems very natural equivalence. If this is invertible, yes. But in general, it is completely positive map, and if, for example, C and C prime equals, there is some functor and natural transformation from identity functor to that functor. This is like a very gauge transformation like thing gives you.
What is C prime?
C prime is another category. But in case this is equals, then you can have the symmetry of category, for example. Symmetry like thing, so transformation.
I think it's called the Rothschild topology, is that correct?
Sorry?
I think there's some physicists called Rothschild or
maybe. I don't have much knowledge about the Hohoshi's homology, but a very young student, mathematical student in Kyoto University pointed out that I think this is Hohoshi's homology, but I don't know. So yeah. Then yes, the same invertible or non-invertible, I think, but some also the state is as a function is correct as I said positive functional, and this is in the machine learning. There is a notion of kernel, and kernel and this positive definite function. Yeah, so the kernel gives reproducible kernel Hilbert space, and yeah, all the machine learning kind of mathematical structure is derived from that. So on the category, so the learning structure on the category is possible. So I think this is quite how to say possible that our learning also has the learning categorical learning. It's just the point is, yes, to check the sameness of Fourier can be reduced to some kind of reversible alpha. So in other words, this is a completely positive map, and so making the using the for example instrument kind of apparatus, we can define this kind of Fourier and the sameness or non-sameness like the phase transition like state change. Yes.
So C is the Fourier structure,
yeah.
and then A is
Ozawa.
and then you are saying that that level of the transformation alpha corresponds to the checking of the sameness of the Fourier.
Yes.
So the Fourier check itself is difficult. This side of it is possible.
Yes, possible. I see. So, and it is a deep. My hypothesis is that it is a deep reason why quantum cognition is useful. Because maybe if maybe someone realized that this category does not have to be the Fourier kind of thing. The more if you are given any category, we can do such a thing. But the point is, for example, actually this is a space-time. If this is causal structure of space-time is given, this is a quantum field theory. So by using these apparatus, we can connect the consciousness studies and the quantum physical research.
Underlying mathematical structure.
Underlying mathematical structure. So this is no coincidence why quantum cognition is important.
But that link that you said is a link between Fourier structure and quantum field theory, right?
Yes.
It's not, where does that quantum cognition fit in here?
Ah,
Non-commutative.
non-commutative, yes. Now, why quantum means here non-commutative?
From the algebraic structure.
Mm.
The non-commutativity is related to the structure of observable, what can be observed. And this is very famous that the Einstein told Heisenberg. Heisenberg initially assumed that you cannot measure the trajectory of the particle. And Einstein said to Heisenberg, what can be measured is determined by the theory. So the theory is fast, and what cannot measure or what can measure is determined from the theory. In this case, you start with category, then what can be measured is determined by the self-adjoint element of this category algebra. So the category determines what can be measured. And then there is a structure of this algebra, commutativity or non-commutative. If it's non-commutative, then this includes the quantum mechanical quantum property, which is related to the Heisenberg uncertainty principle. So this is the answer of the Heisenberg to the Einstein, that the non-commutativity determines what can be measured, what cannot be measured simultaneously. So everything is very general, and quantum mechanics is start with a symmetric group of the system. But in this case, the Fourier structure is much more general. So and the categories, it's very difficult terminology, but it is you start with group, and the groupoid is that the group more general kind of group which has many identical unit. The group has unique element. However, you can generalize this algebraic structure in which the group and has many different units. In this case, you call this group point. And then you consider the semi-group. Semi-group is a unique unit, but not necessarily every element is inverted. Group is that unique unit and every element has inverse. The semi-group is that you can have the product operation, but not necessarily everything is invertible, but you have the unique identity. Then more general notion is semi-groupoid. Semi-groupoid is has a multiplication and not necessarily unique units, so many different units, and still it's not necessarily invert. And this structure is just category. And then such an algebraic structure can be linearly extend, linearizing those product multiplication structure, then you can make algebra. This is just algebra generated by semi-groupoid. And then if you have the evolution in the this semi-groupoid, this can be the star semi-groupoid. This is just a dagger category. And then you can linearize this star semi-groupoid. This is just his star category. So it's a very easy.
Very easy. Yeah, if you ask,
then you realize non-commutativity and uncertainty. So this is the quantum part. So the quantum cognition is natural if the resulted algebra is non-commutative.
Yes.
But if you go to very beginning, it seems that you assume that the brain functions form category. But it's a very questionable assumption. So maybe this beautiful mathematical building is on very shaky ground.
Well,
Okay, maybe you.
Yes and no. Many things are not category, but usually the category of those things. So categories, the usual way of science.
Theoretically, it should be.
For example, if you admit the brain network, then you can have the category very rigorously from this network, because path on the network forms category. So if you consider the path kind of concept, then you have category.
Okay.
So I think this.
Yeah, I think it's very nice because of the categories are ubiquitous.
Ubiquitous.
Structure. So everywhere you can.
Yeah, everywhere you can.
Then his work is that from ubiquitous
Yes.
observational system. So every ubiquitous category
has its algebra. So
category algebra,
yes.
which includes observable. Observable is just what can be measured about this.
But ubiquitous is neither so good. Then for tables,
This is quite very Hilberto kind of. Yes. Yeah. For example, if you are the 1 minute, there is many interesting data categories like so-called cobordism. This is for example, one-dimensional manifold. The connecting two-dimensional manifold. This is arrow, and this is object. Then you have the data category, which is related to so-called topological quantity.
Because your construction is not general enough, but now I thought it's too general.
Oh, okay, but if you constrain yourself to the brain kind of category, the brain-based.
Brain kind
This is a point, but this is I think the dagger category plus some axioms. I don't know these axioms.
Yes.
But this is the first axiom. Like Hilbert's geometry begins with, for example, the 2 lines and 1 point or something. Then, for example, the parallelism. Then this branching. So we need, of course, but
not necessarily monoidal.
not necessarily.
But there's a dual position for what you said about everything being categories being ridiculous. Actually, another way to say it is that the homomorphism.
But there are for the field theory, you cannot describe those categories as monoidal. You cannot do.
Yeah. So what I'm saying is, you don't need categories. Getting back to what I said to you before, many things are not categories, but that's okay. They can be objects in a collection whose morphisms are homomorphism. So it's a dual position too.
Okay, I think I'm very happy to have a discussion, but we need to finish here. And to continue discussion in, for example, Ryoanji or Kinkakuji or something is very nice. So.